Alright, so this is triangle congruence part 2. We're going to learn 2 new theorems and then one that is never ever ever a theorem. And then we'll do some examples. So 2 theorems, the one you'll never use, examples for solving for unknowns, and an example proof. So this one, the angle side theorem, sometimes doesn't get taught on its own because it's an extension of angle side angle. Because of the third angle theorem, which says if we know that we have 2 pairs of congruent angles, so we have these are congruent and these are congruent, well then automatically we know that the third pair of angles is congruent. So this is really becomes angle side angle, which is a proof for a theorem that we've already used. So you can just use angle side, but you could also call it angle side angle. Both of those they're kind of interchangeable. This one is a special case. This one is the HL theorem. And this is only for right triangles. So if we know that the hypotenuse and one of the pair of legs are congruent, then the triangles are congruent. So this is a special case not only because it's only for right triangles, but it's also a special case of the theorem we're never ever going to use, which sometimes gets referred to as the donkey triangle, because you may have realized by now that all of these letters that we've been using, S's and A's, could make a word that some people would find funny if that A moved to the front. Though that is not a triangle theorem. However, let me go back a page. If I were to trace out which sides I have here, I have side, angle. This one works because it's a right triangle. So we can use SSA only when it's a right triangle, and just to make sure we're not confusing it, we call it HL. So if I ask you to prove that 2 triangles are congruent, you will never say SSA. Never. So for example, if we know that 2 triangles are congruent, and we know that these are congruent by side, because we have 3 pairs of congruent sides, then we can set the sides equal to each other, and that would help us solve for the unknown. And we can do the same thing with the x's. 7x minus 4 equals 31. How do I know to match the 31? Well, it comes from the corresponding side with 2 tick marks. So here's an example proof. I'm going to walk through it. We're asked to show that the 2 triangles are congruent, and we know that we're given that the 2 lines here, BR and EV, bisect each other. So if they bisect each other, that means they cut each other in half. So if you cut something in half, that means you get 2 congruent pieces. We get this and this. We also know that we have vertical angles. Notice I marked up my diagram before I did anything else, and I'm going to decide before I do anything else that this is a case of side angle side congruence. So I'm going to start off with my given, and I know that BR and EV bisect each other. And that's our given. From the given, I can say that, that does have a name there. I can say that BA is congruent to AR, and VA is congruent to AE, because that's the definition of bisect. Definition of bisect. Okay, so that's the sides, the 2 pairs of congruent sides. Now I need to name the angles that are congruent. So I'm going to use 3-letter angle names. Angle VAR is congruent to angle BAE because they are vertical angles. And so since I have 2 congruent sides and the included angle is congruent, I can say that triangle BAE is congruent to triangle RAV. And I can say that by the side angle side theorem. So there are 2 new theorems here. Make sure you write down those 2 in your summary, and whether or not there's any special cases for using them. And then which combination of sides and angles is not a theorem, and the one that we'll never use in a proof.